or different mechanisms. And within that context, we actually could subdivide it into different reactions. So in this bottom case, we have what type of reaction happening? Bottom two. We have an elimination. And in the top case, we're looking at substitution. And one of the questions that would come up would be, well, why do we care? Right? Is it necessary to know what's going on with this? Philosophically, yes. Everything we do, we want to know why and how it happens, because then we can potentially know more about our universe. Chemically, is it relevant to what we're trying to do? Okay, well, if we went through and did a substitution reaction, notice what our intermediate is. Okay? We have a secondary carbocation. If we look at the elimination, one of our elimination mechanisms produces the exact same thing. What does that suggest about trying to obtain products in either of those mechanisms? Okay. If I go through and think I'm doing a substitution of that first type, or top one here, and where we generate that carbocation, what is something that could potentially destroy the likelihood of making that product? Formation of the alkene, doing the elimination reaction. So depending on the mechanism conditions, in one case I can do a substitution that might very directly form an elimination at the same time. That means I'm going to want to adjust my conditions, hopefully. So if I know what's happening within each of those mechanisms, I can change the conditions to favor the substitution over the elimination. Okay. If we go through and look at the intermediate two in between, notice there are no extra intermediates. Okay. So the competition between those becomes less direct, okay, because they aren't favoring the same intermediate structure. They're reacting with either a nucleophile or a base. So if I want the substitution in that middle case, how can I ensure that I don't also get the elimination product? Make sure that I don't add a base, because if I add a base, what happens? I start to favor the elimination. Okay? So we want to be able to understand these reactions so that we can then control the conditions under which they form or the conditions under which they react, and we can get different products coming out of them. Okay? So one of the things that we could go through and do would be look at reaction rates. So we've got a couple hopefully quick slides here. If we had that overall reaction, our rate law for that expression is given by the rate being equal to rate constant times concentration of our reactant held to some exponent, typically known as the order, times the reactant, next reactant, to its order, officially times the next reactant times the next reactant, the next reactant, the next reactant. Okay, stop saying reactant times product. The product can officially make it into the rate expression. When does that happen in biochem? Why do we typically not look at that? Because we don't have complex biological systems that feed back on themselves and shut the reaction down. Okay? So when we're looking at our standard reactions, we don't see products affecting our rate laws. Okay? But officially they do show up in the rate expression. Okay? So if we put in C and D. Okay? So what does it mean if we don't actually see them have an effect? Their orders are 0. Anything held to the 0th power is 1, and it disappears from our equation. Okay? So the superscripts, our orders, must be proven experimentally. Okay? And that's kind of nasty. You might remember going through and doing all those experiment rate calculations and concentration changes and predicting orders and all that fun stuff. Okay? The other way we could predict them is using mechanisms. Okay? And mechanisms are ultimately the reverse of doing the experimental result. We go through and say, this is how it works. Does that match what I would expect the rate law to be? If it does, great. I now have a rate law tied to my reaction. Okay. How would I verify that that rate law is valid? I still have to go back and test it experimentally. Okay. So what are our orders? Our superscripts are ultimately the math. The order or the term that's associated with this is an attempt to make that math understandable. Okay? So if we take a look at some kind of reagent orders, if we have an order reagent of 0, it has no effect on the rate. So that species is acting as a bystander, not involved. Okay? Order level of 1, well now it's actually involved in the reaction, okay, because it's not 0. What happens if we move up to 2 or 3? It's becoming increasingly more relevant and important to the reaction. Will we ever see orders in the 4, 5, 6 range? Probably not. Why not?
Organic chemistry. We have organic materials.
Well, just in general.
Just in general.
It's all one thing analytical.
Okay. When we're referencing our order, okay, one thing to think about or kind of evaluate is that that's how many of that molecule is involved in the rate determining step. So at 0, it's not involved at all, so it has no effect. At 1, we're saying that molecule is involved in the reaction. 1 molecule is involved. If we have a rate order of 2, what are we now saying? 2 molecules are involved. Rate order of 3. 3 molecules involved. Rate order of 4. 4 molecules, and so on and so forth. Why do we tend to ignore 4, 5, 6? So simplifying down to 3 is our arbitrary input on it. I don't want to deal with it above 3, so I'm going to make it 3. That doesn't quite work. Okay. It's the amount of these particles getting involved. Okay. How many single people are there in the world? Too many to count. Okay. How many couples are there in the world? There's less. How many threesome groups are there in the world? A whole lot less. How about foursomes? Okay. What happens when we start looking at the number of people that we're trying to bring together to cooperate and do one thing? The more we bring together, the less gets done. Right? Same thing is happening in chemistry. Once we hit 3, the odds that we can get 3 molecules all directly aligned with each other in the proper energy level, in the proper orientation, becomes astronomically small that it doesn't really make sense to evaluate anything with more orders than that. When we're looking at organic chemistry, we're going to be up in that first and second order only. We won't get up into the third order, and we most certainly will never make it into the fourth order. Even the second order becomes questionable for us. Almost everything we deal with is in the first order for an individual reagent. Yeah?
Do you know the interactions that give those for?
No.
Okay.
That's how common they are, or how ignorant I am.
Cool.
Take your choice. Okay. What about order of the reaction? Well, your order of the reaction is very similar. We just take the sum of all the reagent orders and we can then refer to it, okay, as a molecularity. 0 order for a reaction means the reaction didn't happen. Okay, there's no reagents involved. Nothing's happening. Okay. First order means unimolecular, meaning 1 molecule. There's only 1 molecule involved in a unimolecular reaction. Second order, 2 molecules involved. Third order, 3 molecules. Okay. All we're doing is now increasing the amount of molecules involved in our rate determining step, which brings up hopefully the next issue. Not quite the next issue, we'll get there. Okay. If we looked at our rate expressions, I'm not sure how much I like this slide. If we look at this top case, notice what happens on our orders, right? 1, 1, coefficient was 1, 1, right? How about the next case? There's our reactants involved. 2 and, what says 2 in front here? Why is that only 1? Okay. If we go down to the next one, it's NO2 plus CO, and yet when we look at the rate, second order with respect to NO2, and CO is not involved at all in the rate. What's going on? The coefficients don't have anything to do with order in a reaction. In a mechanism, they do. Okay? So when we're looking at individual reactions, it's the big picture. These are my reactants, these are my products. Depending on how that reaction occurs, i.e. the mechanism, our rate expression may have some correlation back to our overall coefficients, and it may not. The only way we would determine that is experimentally. Okay? One of the things that we attempted to do in 152 would be to have you go through and look at an elementary equation, which is ultimately one step in the overall mechanism or the overall reaction that is occurring. So we look at a bunch of the elementary steps. We would look at those elementary steps and decide which of those is the most important. Well, which elementary step in any reaction is going to be the most important step? The absolute slowest one. Okay? Anything after that we don't care about because it's going to be faster than everything else. Everything before that we might need to care about because those dictate how we get the reagents for our slow step. So they will have an effect. And there's different assumptions that you have to go through and make to go through and solve those reactions. So when we're looking at a mechanism, what we want to focus on is our rate determining step. At this stage in the game, we're really looking at relatively simple reactions. We're up to 3 mechanistic steps at most. Okay? By the end of the semester, we might hit 4 or 5. Okay? What you need to do is look at those steps and say which of those is the slowest step. That slow step is going to be relevant to solving your equation and understanding something about how fast that reaction can occur. If you ignore that information, you can prevent yourself from seeing bits of useful pieces. Right? So if we looked at the speed at which you got to campus, let's say it takes you 30 minutes to wake up and 15 seconds to get to campus. Right? Would you get here faster if you changed the speed at which you got to campus? Well, you might, but in comparison to your overall, percentage-wise, it's not much of a difference. So if you're trying to improve the speed at which you get to campus, okay, or from wake up to campus, you need to focus on that get out of bed part, not the drive to campus part. An extra 2 miles an hour isn't going to do anything for you. Okay? But not taking that extra 20-minute nap, okay, might make a significant difference. Okay? So, big important thing, slow step always controls the rate of your reaction. Okay? Every time we look at a mechanism, we will be zeroing in on the slow step. That is the one that's going to help us the most. Okay? So, this is lovely. In experimental evidence, you guys kind of remember this, right? Okay, we run an experiment where we vary the concentrations of our substrate or our reactants, and we want to see how the rate changes. We can use that information to predict the rate expression for this reaction. Once we have the rate expression, we can then potentially come up with a mechanism, okay, or evidence for verifying a mechanism or not. So how do we go through and solve this? So we need to turn this into a quiz. Call this A and B. What are the orders for A and B? You have to look at the table. What do we look at in the table to figure this out? What's that?
Start with the control.
What do you mean a control?
So look at, trial number 1.
Okay, trial number 1.
You have put 1 and put 1 molar on both.
Okay.
And then look at what happens when you double both of those.
Okay.
And see what that affects, how that affects the rate.
Okay, so if I double both of them and my rate changes, does it?
Yeah.
Yes. Which one caused the rate to change?
Doesn't tell you.
Okay, we don't know. We want to only change one thing at a time. So if we compare trial 1 to trial 2,
There's no difference between one and
for substrate A, there's now no difference. So is there going to be a change in the rate due to substrate A? No. So that I don't worry about. But what happens to the concentration of substrate B?
Doubles.
It doubles. What happens to the rate?
Doubles.
It doubles. What does that mean?
First order.
It's first order. Sort of ringing bells. At least to get the idea of where you would need to go back to find the information, do all this solves. Okay. It's lovely. It's awesome. 152. You love it. Great stuff. Do you want to do solves like this on the exam?
Yeah, though. I like them.
Sure. Yeah, it's gonna take up another problem.
Well, it's going to take up another problem. It'll take you half an hour to solve.
I would prefer you just give us.
Okay. So we will not be going through and expecting you to go through and do this. Your textbook talks about it. Okay. It is not worth the effort to go through and do this, because if I write those questions, everybody gets pissed. Okay. And even those of you who are saying, yes, let's do it, don't want to do it. You really don't. Okay. So we would go through and set up our experiments to control how things changed, predict our orders. In this case, when we go through to solve, what do we find out our orders are? 1 and 1. What does that mean? In our rate determining step, both of those species are involved. That's what it means. Okay. So now we could go through back to what we've already talked about on Wednesday of looking at what things changed and how those things could change. Okay. And we had 3 different mechanisms, the third of which we said we could ignore, and we had 2 others. Right? What were those 2 others? Called them 1 and 2. That's not super helpful, but let's get a little more detail than that. We could break our bond, then make our bond. Or we could
Make and break at the same time.
break and make at the same time. I understand make and break at the same time. That actually sounds nicer than break and make. But I like these because we end up with bite me and
Bam.
bam. Just kind of a nice comparison, which we will adjust and move to 1 and 2 here in a second. When we looked at the bite me mechanism, how many steps were involved in that?
2.
2. Which of those steps was rate determining, our slowest step? The formation of our intermediate. So the very first step. Right? What were the reagents in that very first step? Substrate. Anything else? Solvent's not a reagent. Nothing. So our rate determining step had how many things in it? 1. So if we looked at our mechanism result, we would call that reaction unimolecular. Would this experimental evidence support that? No. This one says it is bimolecular. There's 2 reagents involved in our rate determining step. In the case of the break then make, we don't have any evidence of 2 reagents. Okay, so I'm saying some questions, and it doesn't look like anybody's actually looking at their old notes. Let's draw out those mechanisms real quickly. Okay, I'm not going to draw curved arrows just because time. Right? That was our first type. Our second type was doing it all at the same time. Right? Familiar? Okay. And in the first step we said, or the first type of reaction, or bite me mechanism, we said this first step was the only one that was relevant. The second step is irrelevant because that one is going to happen faster. Why would that one happen faster? We're minimizing charge. We would expect that reaction to happen very quickly. So when we look at that first step, how many starting materials are there? 1. If we looked at our conditions from our experiment, we said that we needed 1 and 1. Okay. We needed 2 things involved. There's only 1 thing involved in our first type of our mechanism. So if we were to write out that rate law, we'd get rate equals our rate constant, whatever that is, times structure A. Structure B was our nucleophile. Where is it involved? A later step, I don't care about it. If we look at the second one, what happens? Where's our rate determining step? There's only 1 step. So our rate determining step, by definition, is that step. What things are involved in that? I have both structure A and structure B. And one of each. Which of our two mechanisms explains our experimental evidence? The second one. Okay. We reference these as our bite me and our BAM mechanisms just because of our break then make and our break and make. Okay. Believe it or not, those are not accepted acronyms for these types of reactions. Okay. Kind of frowned upon to run around class saying bite me all the time. Okay. It can be misconstrued. Okay. So we end up referring to these based on the type of reaction occurring. So what type of reaction occurred? Substitution. Okay. What we'll also introduce is that we are using a nucleophile. Okay. Why are we mentioning that? Beside the point. We're using a nucleophile. So we'll call this SN, typically written as a subscript for that capital N. Okay. So substitution, nucleophilic. And then you'll see a reference to a 1. In the other case, it's still a substitution, still using a nucleophile, and we'll refer to that one as 2. What do those 1 and 2 refer to? Number of steps. Okay, in SN1 we have 2 steps. I don't understand your step argument. Look at your rate law. Your rate law has only one thing involved in it. That 1 stands for unimolecular, which comes from understanding our rate law. When we go through and look at the 2, where's the 2 coming from? Bimolecular, because when we look at the rate law, there are 2 species involved. Okay. So what we're going to shift to now is referring to these as SN1 and SN2. Okay. You may still hear me refer to bite me and BAM every so often, but we need to kind of become a little more sciencey. Yes, it's a word. Okay. And bring in our SN1 and SN2 terminology now. The reason we held off so long is we needed to have some context of why we call them 1 and 2. If we think back to the elimination reactions, okay, there were 2 types of ways our elimination reaction could occur as well. Okay. Those get referred to as E1 and E2. Why? For the same reason our substitutions are called SN1 and SN2. Okay. Exact same reason. Kind of makes sense? So what we're now going to do is stop looking at experimental evidence, and we're pretty much just going to look at our mechanisms. And the reason why we're going to do that is that there is experimental evidence to support all 4 of these reactions and mechanisms. Okay? So we're responsible for all of them. Okay? So no more experimental evidence, just now looking at the actual reactions. So if we looked at the SN2, okay, break and make, how would we go through and do that? Generic structure, what do we start with? Actually, I'm going to do this. Yep, that was too much. Right, we need a generic structure to start with. So there's our leaving group. And we're going to need a nucleophile. Okay. What happens? We break the bond between the carbon and our leaving group. So we'll highlight that in red. Where are those electrons going to go? To the leaving group. Okay. So what character? I'm going to bite my tongue on that one. Never mind. What does the nucleophile then do? It attacks the carbon, our electrophilic carbon. Okay. The result. So we end up with our nucleophile, and we end up with our leaving group chilling off on its own. So let's critically evaluate this reaction. You notice the curved arrows I used may not actually be the curved arrows that you would have used. In fact, most people that I've watched go through and do this draw their arrows like this. Okay. I might even see one doing that. What's the issue with the one going to the leaving group? We're trying to form a bond. That arrow now says the nucleophile shares electrons with the leaving group. We're now making a bond to the leaving group. Okay. that would break an octet. So we aren't going to do that. We have our electron going to the carbon that is missing electrons. We will break that weak polar bond with the leaving group. Okay? So characteristics of our leaving group. I just suggested one of them. It's a polar bond. How does it become polar? There's a large difference in electronegativity, which is one of the reasons why it would take the electrons. Whatever that leaving group is much more electronegative than carbon. Okay. What other characteristics might we expect of the leaving group? Okay. Typically, our leaving group tends to be large. Okay. More electronegative, large. What's that? Halogens. Halogens are great categories within our leaving group because they are large and electronegative. Okay. What if it left neutral? Would it be a better leaving group? Yes, you can leave neutral. If it left the structure and was neutral as opposed to being negative, would that be a good thing or a bad thing? It'd be a good thing. For it to leave, it needs to be able to stabilize that negative. Hence, it's electronegative. Hence, it's large. Okay? So we're looking at size. We're looking at charge. We're looking at size. We're looking at electronegativity. We're looking at resonance. We're looking at an inductive effect. Those 5 things all correlated to neutralization or stabilization of charge. We're using the exact same things that we use to define acids and bases as we are defining our leaving group. The leaving group needs to be able to stabilize the negative charge, or the electrons coming off the structure. The more stable those electrons are, the more easily the leaving group can leave. Okay. What can you tell me about the nucleophile? Okay. Has electrons. Okay. Should it be electronegative? So it's typically more electronegative because that's how it's getting those electrons. Okay. So instead of breaking down each of the individual things that made the leaving group great, okay, let's not break down each of the individual things that makes the nucleophile great. Let's focus on its overarching picture. What is the overarching picture for the nucleophile?
It's comparing to the leaving group.
So relative to the leaving group, what?
Smaller than the leaving group.
You're still getting into the specifics. I don't want the specifics.
That's the leaving group.
Can't stabilize the negative charge effectively.
Not a stable negative. So what you were suggesting, smaller. Okay. Why smaller? It doesn't stabilize the negative charge. So if we focus at the bigger picture, we can then whittle back to those same 5 rules and apply those rules to our larger issue of what it's trying to do. Those electrons on the nucleophile need to attack. So we've come up with ways to now evaluate our leaving group and our nucleophile. Are there other things drawn in this reaction that we could potentially be looking at? Could look at the substrate structure. Okay. How is the substrate structure going to affect our reaction? Those of you in lab should be jumping all over answers on this. It's actually going to come back to our mechanism.
Primary, secondary, and tertiary.
So primary reacts faster than secondary, faster than tertiary. Great, you've got a little memorization device now for the SN2. We want our substrate to be really, really small. Okay, primary as opposed to secondary or tertiary. But why? It's going to come down to this arrow. That arrow I drew was not the initial one, and I said that is a questionable arrow to show for this mechanism. Why is that? What does the nucleophile have?
Electrons.
What does the leaving group have?
Electrons.
They are fighting with each other between these two systems. What happens if I bring that nucleophile near the leaving group? They repel each other. Okay? The one that has the stronger bond to the carbon will stay, the other one will move away. Which one has the stronger bond? The leaving group, because it's actually bound. So the nucleophile comes in and it leaves. It comes in and it leaves. That's not a very good reaction. The nucleophile needs to react. Okay? How can it possibly react? It needs to react with the carbon by avoiding the leaving group. It needs to get as far away from the leaving group as it can while at the same time interact with the carbon first. The only way to do that is to come in from the complete opposite side of the leaving group, which would suggest the arrow that I had drawn there is better to be drawn coming in directly underneath. Okay. All we've done to process this is pretty much everything we did in Unit 1. Okay? We haven't even brought in the next level of crap that comes into it that's still Unit 1. Okay? We're building new things upon it. So our nucleophile must come in from the opposite end. Okay? Opposite end is too difficult to say, or not fancy enough, or not potentially funny enough. And so typically what gets referred to for our SN2, it's a little bit more PC than that. Backside attack. Butt end. Backside attack. We're doing a backside attack on our electrophile. Okay? Which means the backside attack must be open. What things are going to prevent that backside attack? Electrons, because the nucleophile is electrons. So the more electrons are on the backside, the harder that reaction is to occur. So we need the minimal amount of junk on the backside. How can we set that up? We can go with a primary substrate as opposed to secondary or tertiary. So what we're adding to our reaction now is specifying the atoms that have bonds to our reactive carbon. That primary structure will react faster than the secondary or tertiary. Why?
There's less electrons.
Why are there less electrons?
Carbon has more electrons than hydrogen.
We look at the difference between our primary, secondary, and tertiary. It's carbon versus hydrogen. Carbon has more electrons than hydrogen. The more carbons we have there, the less likely that attack occurs. Okay? So everything that we're looking at here supports a backside attack for this reaction. Okay? Kind of makes sense? So we make that all pretty. We end up with a system. You'll notice that I added an extra little thing here. I've added a transition state, which was a typo. That should say transition state, for those of you that missed that. I didn't even spell We can just fix that all together. We have a transition state, as we can tell, because of the double dagger in the upper right-hand corner. What is this transition state trying to get us to acknowledge and see?
That they're attached at the same time.
They're attached at the same time, and Stephen, you just added an extra little piece of information here. What's that piece of information? If we add just the hint of more information to our reaction, what is now the issue with our reactant and or product? And Stephen, you can't answer. What is that red carbon? It's a chiral atom, which means when we go through and run an SN2 reaction, Do we need to be worried about that stuff we talked about in Unit 2? Yeah. All that chiral aspect now becomes super relevant. When the reaction occurs, we can see the potential for our chiral atom to change its configuration. Okay. Some things that are a requirement within that. Number one, our reactant had better be chiral. Okay. Not only had it better be chiral, but it should be specified. Can you tell me that this is R or S? No. Until you know that it is R or S, don't worry about chirality because I'm not giving you that hint to tell you that information. Okay? So to change that, you need a wedge and a dash. How does that change our reaction? Anything really look all that different? All we did is change the exact, put in the exact same labels. The next big piece of information, the nucleophile and the leaving group should be the highest priority groups involved in your system.
Wouldn't that change your, whether it's the RNS then? Because if your backside attack and the nucleophiles on the outside of the leaving group, then would it change which direction it's rotated?
If we go through and take a look at our starting material, what is its absolute configuration? It is rotating counterclockwise, that is S. We said our nucleophile was our highest priority in all cases. After the reaction, what do we have? R. We have an inversion in stereochemistry. Okay. So a big complication of the SN2 mechanism is that your stereochemistry will change on you. Okay. So you have to watch out for that. There's a name tied to it. I don't even remember what the name was. Okay. Last bit of information that we haven't talked about. Is there anything else involved in this reaction? Someone mumbled it over there. We also have the solvent. Okay. We're going to hold off on that for another day. Okay. Get through some more of the basics of our mechanisms first. Okay. But that's our SN2. We've seen our leaving group. We saw our nucleophile. We saw the substrate. Okay. We identified an issue with it, our stereochemistry. We've got a lot of the primary differentials between our different mechanisms already set up within this. So what happens when we move to the SN1? What do you think we're going to have to look at? The leaving group, the nucleophile, the substrate, okay, type of reaction, intermediates, transition states. All of the exact same things go into our argument. Okay. If we look at our rate, we end up with substrate times our nucleophile, backside attack. This extra term pops up, steric hindrance. I got a lot of people asking me questions about that from the lab, and I apologize. I should have defined steric a little bit. Steric is just pretty much saying, a fancy way of saying electrons. Okay. So hindrance means electron hindrance. What did that mean in this case? The tertiary substrate had more electrons, which means more steric hindrance. Okay. Steric hindrance becomes a problem in the SN2 because of backside attack. Why do we call it SN2? Two things in our rate expression. Out of curiosity, what do those brackets mean? Concentration. How do you calculate concentration? Moles per liter. Very, very careful with that. You might see some questions popping up along those lines. Moles per liter. That's just from your concentration unit. SN1, break, then make. Do we need to draw it out all kind of ugly, or should we just look at the pretty picture? Ugly. Ugly came first, sorry. So we'll start with the same generic idea, our leaving group. In this case, I'm calling it I and Cl. We don't need to stress on that. We need to break our leaving group bond first. So the electrons go with the leaving group to form a carbocation and a negatively charged, potentially, leaving group. What do we then do? we add our nucleophile, forms a bond with the carbocation, and we end up with our final product. Leaving group. Is it going to be important to this reaction? Yeah. For the same reason it was important in the SN2, it's still important in the SN1. What does that mean about deciding leaving group between these two mechanisms? They're the same. So if you're looking at your mechanisms or a reaction you're trying to decide, is it SN1 or SN2, looking at the leaving group, generally not a good idea because you need a good leaving group for all of these. So don't focus on the leaving group. Okay. Nucleophile. Should we focus on the nucleophile?
No,
Why not? It's still involved in this reaction, isn't it?
it's not in the rate.
Remember, to decide our mechanism, we need to look at the rate determining step. In the SN2, there was only one step, so it was simple. We could just jump straight to it. In the SN1, my focus is only here, which then means my rate will be equal to K times the concentration of my substrate. So what does that mean about the nucleophile?
Doesn't matter.
So all of the things that contribute to an SN2 working, where we looked at the nucleophile, now become irrelevant. That's helpful. We've now eliminated some information. We've shortened the amount of work we need to go through and do. Right? But now we have to evaluate what's going on with our substrate. Okay, well, there's no backside attack in this case. What's going to help that first step go faster? Leaving group we could look at, but we needed a good leaving group in both cases. So leaving group usefulness, probably not so much. Where we should be keeping our focus instead would then be on the piece that's different. We form a carbocation. So when we're looking at our substrate, we're primarily concerned about the carbocation. And what about the carbocation is going to make this reaction go faster?
Ability to stabilize.
Stabilize the carbocation. Okay, and we talked about this again, I think on Wednesday. Everybody goes, well, I don't want a stable carbocation because then I can't form the product. Okay. You're right indirectly, but we still have to form the carbocation for that reaction to occur. If we shift to an energy diagram, our carbocation is here. If that carbocation is incredibly unstable, I may have a very exothermic and very favorable second step, but does the first step happen? No. It goes back to, again, looking at only the slowest step. Okay? So I need a stable carbocation. The more stable it is, the lower that intermediate drops, the faster it occurs. Is that a question? Okay. So how can we stabilize the carbocation? What makes the carbocation unstable?
Positive.
Positive charge. How do you stabilize a positive charge? Electrons. Our first pass, just like we did with our SN2, we looked at our substrate. We said, okay, we need backside attack. We mean the minimal amount of electrons, so the backside is open. What do we need in this case? I need more electrons. The more electrons I have, the less positive it becomes, the more stable that intermediate, faster the reaction occurs. That one is huge for deciding between SN1 and SN2. Why? They are complete polar opposites of each other. If you see a substrate that is tertiary, would we expect SN1? Yes. Why? Stabilize the carbocation. Would we expect SN2?
No.
No, because
Many electrons.
too many electrons. It prevents that reaction from occurring. So by evaluating the pieces of our reaction and ultimately the pieces of our mechanism, we can now start to predict, where am I going to go? Okay. So we looked at substrate, we looked at leaving group. Nucleophile we completely ignored. We could go into the solvent, but there was one more thing that we looked at with the SN2. Okay, if we pretty this up.
Feels like on a ring or something, can't?
No, we won't even look at a ring.
Oh,
Stereochemistry. What happens with the stereo center? Okay, well, so that was a bit mean. What happened with the stereo center? We'll erase that piece too. In our very first step, what happened to the stereo center? It disappeared. In our very second step, what happens? It reappears. How does it reappear? Kind of randomly. The nucleophile attacks what? The carbocation. What is a carbocation? True. Keep going. It's not a stereo center. It is an electrophile. How would we draw a carbocation? There's an interesting idea. We could look at the geometry of that. It's planar, because sp2 hybridized, right? So where's the positive charge? There's a subtle hint here. What changed? Just turned the structure and rotated it, right? And we kind of ignored that other bond. Why would I rotate it? If it's sp2 hybridized, what does that mean is left over? A p orbital with exactly how many electrons in it? 0. What's our carbocation look like? A p orbital. What's the issue with a p orbital? Are there any electrons up there? No. So where could the nucleophile attack? Up there. Are there any electrons down here? No. So where could the nucleophile attack? Down there. What does that do to our product? It gets me 2 products. Okay, so let's draw that out real quickly. The 2 products. That's a wedge, horribly drawn, but close enough. Versus what is the relationship between these 2 products? R and S, also known as enantiomers. When you run the SN1 reaction with a chiral atom in it, you lose chirality because you make 2 products, a racemic mixture. Okay, so there's a good question. I heard someone, we don't want to be. What do you mean you don't want to be? How many products do you want to make every time you do a reaction? 1. So does this kind of screw up our reaction? Yeah, if that chiral atom is important to our overall reaction, that is a problem, which would mean we'd have to go through and purify those 2 away from each other. What if it doesn't have an overall effect on what we want? Then who cares? Okay? So it depends on what we're trying to aim for. In general, the SN1 mechanism is a horrible idea. We do not want to run a substitution reaction using SN1 conditions because that produces 2 products. Okay? That takes our yield from a potential of 100% to now 50%, and that sucks. Okay? But it depends on what we're aiming for. If it matters, then we care about it. If it doesn't matter, we don't worry about it.
It only makes 2 if there's a chiral atom.
So one thing to focus on is it only makes 2 if there's a chiral atom. If there's no chiral atom, we're still getting 2 products, but the relationship between those 2 products would be identical. Okay? The SN1 will always produce 2 products because we have 2 places to attack the p orbital. Okay? The end result is now what is the relationship between those 2 products. If there's no chiral atom, they're the same. There is a chiral atom, they're enantiomers.
You said racemic, but does it always produce a 50-50, or would it produce?
Within the context of this class, it's racemic, 50-50. As soon as you have any chiral atom within the structure or within your solution during a reaction, it will affect the overall results at the end. Okay? So we end up seeing a polarization, and sometimes you'll see it come out at 51-49 or 55-45. Okay? So it's not perfect, but within the context of this class, yes. Questions about what's up there? Okay. So if we looked at our rate is dependent only on that first step. We get the rate constant times our concentration of the substrate. Whoops. Just like with the other one, we could summarize our big statement on what we want to remember out of this. What do we want to remember?
Two different products, or two products.
So we could do with two products. I would argue there's something a little bit more important before that. Because two products we said could possibly not matter if there was no chiral atom. No, not stereochemistry. What? So front end, backside attack are still focusing on that second part, which is still our two products. How do we get to that point where we have the potential for two products? We need to form a stable carbocation. So the primary focus when you're looking at SN1 is you need a stable carbocation. I altered this mechanism slightly because one of the things that you will find is that your nucleophile, because we said it was irrelevant, we don't care necessarily about its charge state. With the SN2, we said it wanted to have a bunch of electrons so that it could react. Do we need a bunch of electrons for our nucleophile here? No. So we could minimize some of that electron density by having it in a full bonding system. Okay, bless you. The end result is that when we go through to form our potential first product, our nucleophile has the potential to become positively charged. Does it want to be positive? No, so what can it do? Some of those initial bonds that we didn't want can be removed in an acid-base step. Okay? So our SN1s typically you'll see them show up with this extra step involved in neutralizing your final structure, okay? An extra acid-base step. Okay, so just kind of watch out for that. So our repercussions, what are our possible products for this? And this will turn into a quiz. So let's do the SN2 first. Is that the correct answer? No, why not? I want you to be careful in saying wedges and dashes. I understand where you're going with that, but we have to be very, very careful with that statement. Did the molecule start chiral? Yes, and we know that because we see four different, good answer, four different things attached. Not necessarily wedges and dashes. I could easily show wedges and dashes, but it'd be a completely irrelevant time to use it. Okay? So we do have a chiral atom, which means we do need to specify chirality in our final product. So the iodine, because we know it's a substitution, is going to do the exchange with the chloride. Why not with the ring, the ethyl, or the methyl? In SN2, there's no carbocation, so I don't accept that.
Chlorine is the best leading.
Chlorine is our better leaving group because it is more electronegative than the carbons of the methyl, ethyl, or phenyl ring. Does that make sense? Mm-hmm. Do I need to draw that? Okay, so what we're saying is a bad product would be something like, oops, let's ignore stereochemistry for the moment. That would be a bad idea because carbon can't stabilize the negative charge. Okay, so when we're looking at our leaving group needs to be the atom that can take the electrons the best. Most of the time for this section, you'll be seeing those be halogens because we've now leveled up from alkanes up into our alkyl halides for reactivity. Okay? So that is a bad product. So now the question, do we need to be concerned about stereochemistry with our final product? Yes. What do I need to change? If I show it wedged, what happened to the stereochemistry? Stayed the same. Within SN2, it needs to exchange, which then means it must be dashed and the other one will be wedged. Okay. Make sense? SN1, what happens? We form a carbocation, which then means the iodide can attack from both sides, which means we should be drawing two products. How many of you drew two products? Okay. In your heads might be a good answer to that. Okay. So, I'm only going to draw one product by saying nice little simple dodge. Does this work for the exam? Absolutely. Okay. All we're saying is that I formed one of my products and then I want the enantiomer of that product. Okay. So it is still getting us two products. One is R, one is S. It's still set up, all that's happening. And as far as comparing the structures, which you might be doing over there, do not compare these structures to each other. All we're doing is drawing that on and then saying, I need another structure here. I need the enantiomer. All I need to do is redraw this and exchange the wedge and the dash. Okay. Make sense? Is that what you were asking about? You're good? Okay. Any questions?
So the exam, for the SN1, you want us to draw the step where the carbocation is formed before we do the process.
So, good question. Do you need to show the carbocation? Do you need to show the curved arrows?
Will depend on what you say.
Depends on the question asked. What's the question asked? Final products, which means I don't need the carbocation, I don't need curved arrows. Okay? To get credit. Okay? And that is another important distinction. To get credit, all you need is right there. Okay? To get to that answer, did you have to draw a carbocation? Then in your case, absolutely, draw the carbocation every single time so that you can see it and you know what's happening. Okay? The more you write, the more likely you will get the answer correct. The less you write, the more likely you will get the question wrong, even in a multiple choice. Yes, of course.
Listen to, why did the iodine become dashed?
We needed to change the configuration. So there's two ways that we could draw this product. Actually, no, there's not two ways in this case. The iodide comes in from the back side of that chlorine leaving group. Actually, we could attempt to draw this. Okay, where is the back side of that chlorine leaving group? Well, if the chlorine is wedged, the iodide had better be dashed. Okay, that's why we need to draw the iodide dashed.
It's coming in from the bottom.
It's going away from you. It's behind the plane of the paper. Yep. So remember we talked about Unit 1 and, for that matter, Unit 2, spatial awareness? That's all coming in here. Okay. In a multiple choice exam, what you might see would be this top answer, and then you might also see this same structure, but picked up and flipped over.
It's not nice.
Sorry.
So now we're going to correct it.
Yeah, it's so hard to see.
Okay. This is why we talked about spatial awareness in Unit 1 and Unit 2 and working with model kits. This is your correct answer for the SN2. But it didn't change configuration. It did. We picked the structure and flipped it over. Not only that, but we could be even more obnoxious. Sigma bonds are freely allowed to rotate, but as soon as I do that rotation, now it looks even further wrong. Because you're like, oh, well, there's no chemistry happened there. I'm not going to worry about it. Still no chemistry happened there, but we just did a sigma rotation. Okay? So you have to be aware of each of those permutations. You have to be looking for them. Make sense? Okay. Believe it or not, I don't do that all that often. Typically, it's just a one-for-one transition. Okay. Visualization of this. Okay, what is the carbocation hybridization? sp2. Okay. So what we're looking at is if we added a p orbital to that structure, what does it look like? Never mind. Oh, I must have just done some weird edit. Okay, as it's drawn, the draw on that carbocation is coming in and out of the plane of the paper at you, which is incredibly difficult to visualize. So in that previous case, what I ended up doing was rotating it so that we still have our trigonal planar system, but now we can see the p orbital. That p orbital is what's causing the nucleophile to be able to attack from the top or the bottom, which is giving us our inversion. Okay? The way the textbook has gone through and done it is turned it on a different axis, where it's now coming kind of completely out of the board at you, which then means your p orbital is where? It's going sideways. There's two locations for the iodide to attack, which means we end up getting two products. So it's just another way, an attempt to get you to visualize and see what's happening within those structures. Questions? Okay. Visualization here, not the easiest again. Okay. What we're trying to do is look at our transition state. Okay. The iodide comes in and must align on the back side of that leaving group. Okay. So what ends up happening to the other bonds? Okay, what we have, I can do slightly better, this is great for people at home. We take your hand and turn it into a tetrahedron. My wrist is my leaving group. My, index, middle, and thumb are the bonds, or the other three bonds. So if my wrist is the leaving group, it starts to leave. Unfortunately, I can't separate from my hand, or fortunately. But where does the nucleophile then come from? If it comes from the top, electron-electron repulsion. It has to come in from the backside. So as it comes in from the backside, what does it encounter? Electrons, which has potential for chasing it away. Okay? But if the iodide has the proper orientation and enough force, that could have been really bad. I didn't stop fast enough. It can come up, form the bond, and kick the leaving group out. But then what happened to these groups? They must repel away from it, which I can't really do, but that would kind of be like popping upwards. That's about as far as I get. Okay. What we're seeing is kind of an umbrella in the wind. Okay. The wind comes, catches, and flips the umbrella the other direction. So when trying to draw that inversion, you have a couple options. You can draw the structure exactly as it started, but then just show your nucleophile being in the opposite plane of where your leaving group was. Or what you can do is just pop the rest of the atoms kind of away from it. So if we look at our shape, oh, they've actually drawn it there with the umbrellas. If we look at the shape of those three atoms, they're kind of cupped this direction. When the nucleophile comes in, it acts as a big gust of wind, which then pushes them back the other direction. And notice when we look at their shape, they've changed the orientation. Okay? So what things might change how that reaction occurs? Well, one thing we already talked about, if those groups were carbons instead of hydrogens, what do they have more of? Electrons, which means when that gets near, it goes away. What happens if I make that bond up top longer?
Pull those bonds more like
Those bonds now have more space. Okay? The reason we're in a tetrahedral structure is because all the electron groups are equivalent. As soon as we make one bond really, really long, what happens?
more space.
Not all equivalent. More space means,
They have more room to spread around.
which means what happened to the backside? More exposed, faster reaction. What if we had a very short bond? Now the backside, very well protected. Okay. So subtle changes in our structure and our hybridization can prevent or allow different reactions to occur. Okay. Elimination reactions. Okay, I know there's a lot up here, so let's see if I can't simplify this. If we went through to do an E1 elimination, so if this was our starting material, the leaving group leaves, we form a carbocation, and then we have to pull off the hydrogen. How do we pull off the hydrogen? The electrons in that carbon-hydrogen bond need to go where? Need to go to the carbon. What would help break that hydrogen off? It would come off as a proton, so what could help facilitate that? Some sort of base. Okay. Turns out we won't need a base in this case because that's not our rate-limiting step. Our rate-limiting step was forming the carbocation. So we can't bring in a base because the base isn't involved in the step. So how can I weaken that bond? Heat. At enough heat, that bond will vibrate enough and cause the electrons to shift over. Okay. So we now have a carbocation. That's an eraser. Let's try that again. There's our carbocation. We have our wedged pH4 phenyl, not phenol. I know, subtle difference. Another pH, and our hydrogen. For this reaction to occur, the electrons in that bond between the hydrogen and the carbon must go to our carbon in such a way where they overlap with what? The p orbital from our carbocation. What is special about the p orbital? Same things for the SN1 reaction. Where can we put electrons? Into the top or the bottom. Does that change our product? And in E1, yes it does. So what you should go through and take a look at is that in one case, you'll end up with the product shown up top. In the other case, you'll end up with the product shown down below. Okay? The only thing that changed, can I do this? Yep. Is that we do a rotation about the sigma bond, which is a perfectly valid maneuver to go through and do. Because as long as the pi bond's not there, I can do that sigma rotation. So what's going to cause that sigma bond to stay in a particular conformation long enough to break the hydrogen off? Can we do a rotation once we've formed the double bond? No. Okay, not easy to go through and do that rotation. So what is the difference between these two products? Stability, good answer. Cis and trans. What does cis and trans have to do with this? Trans was more stable. Why is trans more stable than cis? That phenyl ring happens to represent a lot of electrons. What is the other one? A lot of electrons. What do those electrons want to do? Get as far away from each other as possible. So we could actually shift this into a Newman projection to visualize the cis product very, very high in energy. If it is high in energy, what does that mean about the likelihood of forming it? Less likely, and we end up seeing instead trans product. So when we do the E1 elimination, it's an interesting feature. We have the option to get two products, both the cis at the bottom and trans at the top, just like we did with the SN1. The issue is that there's another piece of information preventing potentially one of those products from the other. Okay? That issue comes down to cis-trans isomerism. Trans is lower in energy, so when we run the E1 elimination, if we do generate a product that exhibits cis-trans isomerism, we end up seeing a large favoring for only one product. That one product being trans. Okay? That's what this whole slide is trying to go through and show, or what that whole figure is trying to go through and show. Okay? They're showing these subtle rotations about the sigma bond after we've lost the leaving group. Okay. And I think, did I do a Newman projection? I did not do a Newman projection, but I did at least show the p orbitals. So if we've got our p orbital system up top, okay, no further rotation, we have the exact same system. What happens with our electrons? The electrons can rotate directly or donate directly into our pi bond, and we end up with this weird kind of drawing here, but if we flatten that out, we see that we have the trans product alignment. If we rotated further, what ends up happening? Our hydrogen is now located at the bottom of the structure, which means when the electrons shift over, we're now locked into our conformation. What happened? We end up with the cis product. Okay. Did I really not show a Newman projection? Okay, well with the last like 30 seconds, I'm going to attempt to show a Newman projection for these. So this one, we're going to cite left being the front. Sorry, I got to draw the right way. Phenyl CH3, back atom, phenyl H. Everybody see that? If we take a look at the other one in purple, and again, I know it's stupid, but I gotta do it. Phenols, CH3, phenyl H. Okay. When we go through to do the elimination, we're looking at the hydrogen on which are front atom. The hydrogen must be aligned, this can become important for our E2, aligned in the same axis as our p orbital. Why? We're trying to make a pi bond. To make a pi bond, p orbitals must overlap. Okay? If we look at the other situation, our hydrogen, whoops, was rotated to the other side, goes to the top. We're still putting the hydrogen in that p orbital axis. Okay? And it looks like I drew the hydrogens on backwards. Okay? That's where we will end, and we will pick up